right, so I'm receiving any emails in advance or any questions. That kind of makes sense because you just came off your exam and you probably don't have any questions about the new material. Spent this morning grading the exams. So if you check your exams and you see the work, there's a 1 out of 1. That means I've gone through and graded your exams. Please look at the test directions. It tells you I'm going to respond to some emails this morning, but I got a lot of emails saying this week. I'm like, well, what about my grade? It's like, this is why you need to wait until I grade your exam. Blackboard is just a blind algorithm. So let's say the answer is 2 and you put 2 kilojoules per mole. It's going to count that wrong. Your answer is still correct. You just put kilojoules per mole in there so it doesn't understand, so it's giving you a 0 for that assignment. So this is why you need to submit the work, because with the work you can get the partial credit. If you don't submit work, I can't give you marks for the free response questions you got right, because those free response questions require work to justify the answer. The answer is actually not worth that many points. Now, what you'll also see on your exam is feedback. So I'm not sure how it shows up on your end because the student view and my view are a little different. I can't really give myself an exam and grade it. I mean, I'm sure there's a way to do Blackboard. It's really complicated. But you should see feedback specifically where you lost points on each question. So if you don't get the full marks, you'll see a comment like question 12, this is what you missed, or question 14, this is what you missed. But now that they've been graded, send me the emails if you got a question about your grades. This is the first exam. Hopefully you're beginning to see now how to study for these exams, specifically like those homeworks and those packets are particularly useful. There's a one-to-one correspondence between those questions on the packets and the homeworks to the questions that were on the exam. So I've got the chat menu open. Again, this is office hours. These are not lectures. So the reason I do the live streams, it gives you higher quality video so you can actually see what's going on behind me. But unless there's any questions, I'm just going to kind of be responding to emails this morning. Good morning, Dia. How are you? I'm doing well. We're actually getting into the more interesting material now, which is kinetics. Yes, first, second, and third order reactions. So there's a few different things when we talk about with order. So if we ever write a rate law, let's say we have three reactants, A, B, C, purely hypothetical reaction. The brackets here refer to concentration and molarity. The order is whatever power we're raising the concentrations to. So since we're raising A to the first power, it is first order with respect to WRT A. It's first order with respect to B. It's second order with respect to C. And let's say there was some reagent D, then we would say it was zero order. And the reason we get zero order is that we have a property of exponentials that any number A raised to the zero power is 1. And I think you can actually prove this. I think if you take the natural log of both sides, you get A, 0 ln of A equals ln of 1. ln of 1 is 0, and ln of A isn't 0, so that's where that property comes from. So that's how we determine the order. Now, there's also overall order. So overall order is the sum of all the individual orders. So it's 1 plus 1 plus 2, which will give you an overall order of 4. Now, the reason we concern ourselves with orders is they give us a feeling for how stiff or responsive a reaction is to a given reactant. So if you look at our, so 0, first with respect to A, 0, second with respect to B, if we double A, we're going to double the rate. If we double B, we actually get 4 times the rate. So this actually gives us a lot of implications in terms of the, yeah, like it's really that straightforward. What I love about reaction kinetics is, like, honestly, there's a lot less take my word for it with these types of reactions. The only take my word for it you're going to have to do is with the solutions to zero first and second order reactions. So we haven't gotten there. I seriously doubt that you're to this point yet. But if we know that, let's say we have R of A, the rate of A is minus K concentration of A, then the concentration of A versus times is the concentration of A starting concentration, e to the minus kt. So that k there, t in terms of time. And we can prove this all for 0 and second order. And actually, there's a general solution for any order other than 0. We can prove any order other than 1, we can prove exactly what the order is. And the 1 is just a special case. And the reason you have to take my word for it is because we're not required calculus for this course. But that's because RA is just the derivative of A with respect to time. So how does that work? It's actually, so we had the general form R equals K A B. And let's say we have A plus B goes to C. So this is something that kind of gets lost when we take the calculus out of this course, but we can kind of still approximate it. And so RA here is really the change in A over time, which we can write, even though we shouldn't, as delta A over delta T. So what we expect is the change in the concentration of A to be negative because it's reactant. As we start reacting it away, we expect the concentration to get smaller and smaller. So we can crudely approximate that the concentration of A is just the change in the concentration of A. Starting concentration plus the change. And we expect the concentration to go down, so we expect the change to be negative. So RA here is going to be negative K A B. But when it comes to something like the product C, RC is K A B. And again, it's because it's the change in C over the change in time. So we expect the change to be positive. We expect to finish with more than we started with. Now, this becomes a lot more apparent when we actually start solving this with calculus. So let's just say we had the form R equals K times A. You would get dA dt equals minus K A. When you solve, you get dA over A equals minus KT. We'd integrate 0 to time, concentration of A to starting concentration to whatever concentration we get. And again, the negative here is going to reflect the fact that we're expecting the change to be negative. We expect to lose some. Now this is also, so this is the weird thing about reactions. So let's say we have the reaction A plus 2B goes to 3C, and we have our general rate form A equals K A B squared. So beside each of these reactants we have are called reaction coefficients. And they're given the symbol nu sub I, where the I corresponds to what it is. So nu sub A is 1. Nu sub B is 2, and nu sub C is 3. So this is the way we like to think about it because it makes a lot more sense. Formally, they're actually defined as negatives if they're reactants and positive if they're products. So the rate of I, any species I, is just its reaction coefficient times the starting rate law R. Now the reason why I don't like to teach these negatives is because it confuses you when you start writing these equations. So this is why I say just know that if I is a reactant, it's negative. If I is a product, it's positive. Now the nice thing about starting with this form is that you only have to derive the rate law once. Now if you want to know R sub B, that's a reactant, so it's negative. Nu sub B is 2. And then we just got a rate law A B squared. Yeah, you're welcome. So you're gonna have to learn how to derive these R equations two ways. The first is from theory. And the theory is the easiest, but it's also the least successful. So the theory you'll see the assumption an elementary reaction. And Rx in here is reaction. So when we say an elementary reaction, what it means is an elementary reaction doesn't have a mechanism. It is what it is. So the mechanism is the reaction itself. So something like CH4 plus O2 going to CO2 in water, that's definitely not an elementary reaction because we had to break the CH bonds, we have to break the O bonds. It's very likely that this is not what's going on. But something like a redox reaction, where literally they just have to bump into each other to make the reaction work, this could be said is elementary. But the problem is we don't know reaction is elementary looking at. So you're going to have to see the assumption here in elementary reaction. But let's say we have nothing else to go on. So if we have nothing else to go on, we have a reaction CH4 plus 3O2 goes to CO2 and H2O. We would say that the rate of reaction R is just K, and we're going to take all the reactants CH4 and O2 and raise them to the reaction coefficients. So for an elementary reaction, that's super trivial. You look at what the reactants are, you look at what's beside them, and you raise them to those powers. And there's actually a very good justification for this. So the rate here depends on two things. First is the probability reactants find each other. So these are probability statements. The probability of CH4 finding 3 O2 molecules. So you've got CH4 and O2 and O2 and O2, so that's where this all comes from. The K here is the probability they'll react. And so the probability they react, there's a lot of theories that are used to describe this. The one we're going to stick to in this class is called transition state theory, or TST. TST, temperature dependent. There is a very good theoretical justification for TST, and most theories that we use now are just refining TST approximations. So from an elementary reaction, R is really straightforward to derive, and then if you want to find the value of R, you would just plug in concentrations in K. The other way is to derive it from experimental data. And this is what's called the apparent order. So we call it an apparent order because we don't have a theoretical justification for what we're doing. We are basically, this is engineering, we're going to basically say apparently in this range it looks like this. And there's two methods to do this. The first is called method of initial rates. Or MOIR, and the second is graphical analysis. Now, these both have give and takes. Method of initial rates is the least reliable, but it's also the most practical. Graphical analysis is the more reliable method, but it's a lot harder to do in practice because you can't necessarily shift concentrations very easily. And there are assumptions that basically the concentration, the thing you're trying to look at, needs to be the only thing that has its concentration changing. So with both of these, we have to assume a rate law. And that's where the first part of the apparent comes from, is we're going to assume R equals K, A to some coefficient, B to some coefficient. And then we have to fit the data. And this is another reason why we have the apparent, because, and this is a fun thing to love to do, really piss off engineers, is Michaelis Menten kinetics. So with Michaelis Menten kinetics, I'm sorry, I'm going to have to erase this. We've got the rate versus concentration of A. And the rate does this because the rate law is K, R equals K, concentration of A over 1 plus K, concentration of A. So if we measure the rates here, it looks first order. If we measure the rate up here, R looks 0 order, and if we look at it here, R looks like some number between 0 and 1, or the order of A is between 0 and 1. So this is the other issue with doing it from experimental data, is we don't necessarily get nice clean integers. And there's a reason why you shouldn't get nice clean integers. Basically, you don't get nice clean integers, one, because statistics are noisy, and two, experiments are noisy. The second is that your assumption of the rate law may not be right. So these are the two ways we find them, and you're going to learn them over the next 2 weeks. But going for the reaction is the easiest. But again, you have to assume the reaction is elementary, and generally speaking, that's a pretty bad assumption. You can do it from the data. When you do it from the data, you're going to kind of be limited to whatever assumptions you made in the data you're working with. And again, it isn't necessarily practical. You're welcome. The thing to keep in mind with what we're going to be doing with kinetics is that you don't really have to take that much for granted. So if you need an explanation, it does exist. Like there is nothing with the material we just came off of, like the osmotic pressure equation, the boiling point change equation. Like there's a lot of these are just kind of somebody measured in a lab and this is what they got. I love kinetics because there is a lot of beauty to what we're doing. There's a lot of proof behind what we're doing. What I would normally do during a CETA course is I would bring in, I have 4 books on kinetics. I had 2 from college and 2 from grad school. And we start this section out by saying we are not doing pure and applied kinetics. So if you could go look at Wikipedia's discussion of kinetics, you're going to get a lot of information because there is a lot of information out there. This is introducing you to reaction rates. That said, everything we are covering in this course, and I would show this to you in the course, is always in chapter 1 of these books. So it's not like you're learning this material and you're never going to see it again. If you take higher level chemistry courses, this is going to come back and it's always going to start with parallel reactions, elementary kinetics, and analyzing data. And we just get more sophisticated in the things we're saying. So this is kind of like if you were taking a foreign language, this is the intro to the foreign language course. You're going to learn a few basic verbs, you're going to learn some basic sentence structures, some basic nouns, adjectives, and this is going to carry you into a higher course where you would cover it a lot more in depth. And particularly with chemical engineers, like this is the bread and butter of what they do. That R, that rate shows up in every single design equation. It is everywhere. And if you can't find it, you are completely dead in the water. So I will explicitly state assume it's elementary. Never ever make the assumption reaction is elementary. Even those trivial reactions generally aren't elementary. So you'll say something like assuming a reaction is elementary. I've gotten pretty good about correcting that on the exams and the packets, but yeah, it will be explicitly stated assume it's elementary because that's the only way to derive it. But I also don't want to get you into the bad habit of like, oh, I'll just pretend it's elementary. It's like there are definitely like most reactions are not elementary. Some have like 90 steps in their mechanism. You can never look at a reaction and know it's elementary. Like there are weird things that go on with life. I forget which reaction it was that they thought was super elementary, and it just is not. Um, I can't remember off the top of my head. There's a lot of reactions that look trivial that are absolutely not trivial reactions. But the nice thing is, like, if you know a reaction mechanism, so let's say you have catalytic decomposition. So let's say you have catalytic combustion of hydrogen, oxygen, on water using a platinum catalyst. If you know that this is the reaction mechanism, each of these reactions are elementary as written. So by definition, each step in a reaction mechanism has to be elementary. You can't split it any simpler. So this actually becomes the basis of deriving the overall rate law, because you know that the rate for each reaction, you can write out a rate of reaction. So for the rate of HPT, we've got K times the concentration of H2 times the concentration of platinum minus twice 2K3 concentration of HPT, concentration of OPT. So you can write out a rate for each of these individual components, and from there you can make assumptions to derive the larger rate laws. So still being able, if you know how to write, if you don't know how to write these elementary reactions as rate laws, then you can't do things like the quasi pseudo steady state approximation. God, what's the other one? There's one about rate limiting steps, but basically everything you're learning, like even though we'd rarely encounter a elementary reaction here, in the mechanism they're all elementary, so we can derive rate laws for each of them. And in a higher kinetics course, you actually use that to derive the rate law in terms of H2 and O2. And that's how you end up with non-power law kinetics. So things like Ehley-Riedel and Langmuir-Hinshelwood kinetic models, we don't talk about them. They all come from doing what we're doing right now, though. Again, this is why it's like a whole semester long course, is because of all the stuff you can do. Hey, you're welcome. Yeah, enjoy your week too. I'll see you tomorrow or later this week. So I'm not really seeing any concurrent viewers left. So what I'm going to do is I'm going to take off a little bit early. I'm still going to do work, but basically I'm going to switch to a computer that's a little bit better for handling what I need to do for the course. So thanks to y'all that were able to show up today, and I will see y'all later this week.